Now we will look at transformations of functions. There are three that you need to know about: translation, reflection, and stretch. And we will start with translation. Imagine the graph x squared minus 2x plus 1. And on a graph, it would look like this. Now, let's look at a few points here. This is at 1, which is 1, 0. Here we have 2 squared minus 2x is 0 plus 1, so that's 2, 1. Then 3 squared minus 3x, that's 9 minus 6, so this is going to be 4. Right, and then obviously it's symmetrical, so then we've got minus 3, 4, minus 2, 1, etc. Okay, and now we then imagine the graph x plus 3 squared minus 2x plus 3 plus 1. And so what this is saying is, for example, if we have a look at 1, previously we had 1 squared minus 2 times 1 plus 1, and that gave us 0. And so what we're saying is, say it equals 0, we're now assigning the output of x to x plus 3 instead. So or is it the other way around? No, yes, we are saying that we have changed the sorry, I got that the wrong way around, I do apologise. We have changed x to x plus 3. So what we're saying is x, what used to be x, we're now going to give you x plus 3. And if we specifically say 1, the graph, this transformation is pretty much saying, hey, number 1, we are trading your 0, which is the initial output, for the output of x plus 3. And which is, let's have a look, so that's 4 squared minus 8 plus 9, so then this will be 4, 9. We're giving you that. What will that look like? It'll look like that, won't it? And then, so if you keep going along, say they say to 0, oh, oops, sorry. That'll be 0, 1, and that's minus 1, 4. And so what if we go to 0 now? It'll be like, hey, 0, we're now instead going to give you 3's 1. So they'll give them the 4. And then that'll just keep on going. 2. Oh, we're going to, hey, minus 1, we're going to give you what 2 has. Which is 1. And notice that when we keep doing this, we have just shifted everything 3 to the left. Now what if we did x minus 3? So i.e. we've translated it 3 units to the left. But what if we did minus instead? Well, it'll be the opposite. So we would say to 1, oh, hey, 1, we're going to give you minus 2's old number. So then that'll go there. And they say to number 2, oh, we're going to give you negative 1's old number. And same to 3, and then number 4 will get that old number, and then we get that, and which is just a translation to the right. So therefore, we can say that f of x minus a is f of x translated a to the right, and f of x plus a is f of x translated a to the left. And so essentially what I want to say is, if you want to translate a function to left or right by a certain number, put a bracket around the x and then put that number in within it. And then that'll be opposite to what it would look like on a vector, because this would be translation by vector minus 3, 0, because in vectors going to the left is negative. And then over here would say translation by vector positive 3, 0. And these two opposite signs. So sometimes that can be a bit hard to work your head around. That's horizontal translations. Let's have a look at some vertical translations now. And we can essentially use the same concept, but honestly, let's keep it simple. Y equals x squared. And we'd say this is equal to y. But what if we did that's now equal to y plus 1? Essentially what that's saying, if we rearrange it, minus 1 equals y, it's saying that, okay, at 0, at any x value, we'll square it, and then we'll just take away 1. So we'll move 1 down. And so that's why you literally just get, it's simple. This is a translation by vector 0, because you haven't gone left or right, but minus 1 down. And you could also do x squared plus 1, and you get that. And that's a translation by vector 0, 1. The vertical transformations are a lot easier to get your head around than the horizontal ones. But that's translations essentially. So we could also extrapolate this and combine the two and say f of x minus a plus b is f of x translated by vector a, b. And this is, when you describe a transformation, you want to use that sort of phrasing. Next, we will do reflections. And they can either be in y-axis or x-axis. So let's take a look at our previous example of x squared minus 2x plus 1. And let's imagine if we multiplied all of it by negative 1. And this should be easy to do, because, I mean, look, think about any input you do, you carry that out, and so you would get something like this. But then you just make it negative. You just change the sign. That's going to be 0, but then it's going to start looking like that. And that has simply been reflected in the x-axis. Don't get confused. It is a vertical flip, but it's reflection in the x-axis, and that's what you need to use. But what if we only did, putting in brackets, only did the x values? Well, you'd end up with this if you expanded. But more importantly, just think about what you're doing. You're saying, okay, like we did with the transformations, we're saying, hey, x, we're just going to give you what minus x has. So we're saying, hey, you, this fella here, your opposite guy, well, it's roughly equal, we're just going to give you his number. And then it's the same thing. Hey, we're just going to give you this. Hey, we're just going to give you this. And then you just get going all like that. And then ultimately you end up with a reflection in the x-axis, in the y-axis, sorry. See, even I get confused with this. Reflection in y-axis. And then the third one that you need to know is stretch. And you draw your axes. And we're using the same one, x squared minus 2x plus 1. And what if we imagine we multiply everything by 2? And that's like, okay, we've gone through everything. We've x squared minus 2x plus 1. We've done it. But now we're going to double it. We're going to double that output. So now this is going to go all the way up here to become this. Then here, we're going to double it like that. So I double it, just keep doubling it. At 0, it's still going to be 0. Let me trying to make this a bit parabolic there. And if you think about it, it's actually been stretched out along the y-axis. So we would say this is a stretch parallel to y-axis by stretch factor 2. Because we've doubled everything, we've made the graph, it goes infinitely onwards, so it's hard to imagine that we've kind of stretched it out 2 times. But yeah, I mean, just can you imagine that, how you've pulled it out and it looks like that? Anyway. Now let's think about what if we instead just multiplied all the x values by 2. And it's exactly the same thing as before. We're saying, oh, hey, x, we're going to give you what 2x has. And it's the same thing. This guy will get this guy's thing. And then it will continue like this. And the effect of that is you've squished it. You've actually squished it, or you've stretched it by a fraction. One half by a factor of 1/2, which is 1 over 2. Oh, and so I should, going back here, I'll say minus f of x is reflection of f of x in x-axis. F of minus x is reflection of f of x in y-axis. Down here, a f of x is f of x stretched parallel to y-axis by 2, a factor of 2, I should say. And then f of ax is f of x stretched parallel to x-axis by factor 1 over a. And now we should think about what happens if we combine some of these. Combinations, combining transformations. So what we can do is think about it, split it up into vertical and horizontal. I can tell you that whatever horizontal transformations you do, it doesn't matter, and then you also want to do a vertical transformation, it doesn't matter when you put the vertical transformation into play, because horizontal and vertical transformations, their orders don't affect each other. But the order of horizontal transformations affects the horizontal transformations, and the order of vertical transformations affects the vertical transformations. And here is it's really just something you need to be mindful of, and especially when you're doing your horizontal transformations, bracket your x's. That will save you most of the trouble. But I can give you some advice on how I approach it. Vertical, if I give an example like x squared minus 2x plus 1, and I want to translate it up to, so I add that to, but then I want to stretch it as well. Well, oops, I haven't I've translated it up more by 5 because of that stretch. So if I only wanted things to move up by it would eventually get you if you wanted to only move it up by 2, then what I should have done is done the stretch first and then add 2. So that's why I generally say stretch or reflection first. And a reflection, you can think about it as a stretch by -1. And then I do my translations last. And then for horizontal, it's the opposite. I tend to translate first, and then I do the stretch or reflection afterwards. For example, if I'd go say I want to do if I did the stretch first, and then I did my transformation, this wouldn't be translating it 3 to the right. It would actually be translating it 6 to the right. What I should have done instead was this. Like that. So that's why I say translation first, stretch, reflection after. And on a final note, I teased earlier about using transformations of functions to see why the vertex works. So if we take this graph, which is y equals x squared, and then we translated it to the right. Remember, we do our horizontal translations first. We'd make it like that. And then if we applied our vertical transformations, I'm doing this deliberately to match our completed square form. It doesn't change where that vertex is, because that vertex is still on the axis, so it doesn't change. So it'll just be stretched upwards. And then if we finally did this, it'd be translated out like that. And then this vertex will have those coordinates A, C. And that's why that vertex formula works.